All right, the second question on this handout, we'll put the question back in view here. We've got a line spectrum from magnesium metal that registers a line at 266.8 nanometers. We want to first find out what's the energy of a single photon of this emitted electromagnetic radiation, which is just another expression simply for light. And second, we want to find out what is the energy of a mole of photons of this radiation. So let's get this out of the way. And remember what a line spectrum is. Instead of something that's looking like the continuous spectrum. Sorry, I couldn't think of the expression for a moment. Oops, that's running dry. Yeah, so instead of the rainbow, basically, where we don't have any divisions, just one color smears well into the next, we project it on a wall, and we've got strips of color like I showed you in class, like we saw in class, and there are some gaps in the spectrum. So actually, as I watch the camera recording this, I'm just sneaking a peek at the screen to make sure that I am staying within the view of the camera. I'm noticing these ripples of light going through. Oh, I've just extinguished it. So that's interesting. It's picking up the 60 hertz noise of the light bulb. So anyway, it may come back. So let's say, for example, that this line in the spectrum, hypothetically, has a registration at 266.8 nanometers. So that is the wavelength. If you're told that, then that is the lambda value or the wavelength of that line in the spectrum. All right, and I forgot what we were asked for first. What's the energy? So this is very straightforward. E is equal to hc over lambda, and I know it's also, of course, equal to h mu, but I'm going to use this formula for energy because I have both of these constants. Remember, they're on the first page, and they would also always be given on a test or exam, and the lambda is given. I just need to convert it to meters. And so, yeah, oh, sorry, I hit the light. So just remember that this is this describes the energy of a photon of light. And light, of course, we describe as electromagnetic radiation, right? The electric field, the magnetic field, orthogonal to each other, moving as a wave, but behaving as a particle, which we call a photon. And so let's find its energy. Planck's constant, 6.626, sorry, that was messy, 6.626 times 10 to the minus 34 joule seconds. That's multiplied by my speed of light, 2.998 times 10 to the 8 meters per second. And that's all over the wavelength of 266.8 nanometers, and convert that right inside here. I have 10 to the 9 nanometers inside 1 meter. And seconds will cancel, nanometers will cancel, meters will cancel. My answer should be in joules. Put that into your calculator. And what did I get? I have 7.44 times 10 to the minus 19 joules. A couple of things. The original precision was 4, so I've just lost the number on the calculator, so this should probably be 4 sig figs officially. And the question was asking what is the energy of a single photon emitted, so that is my answer. And again, just to further qualify this, this is how many joules it is per single photon, or per photon. Let's assume that it's one. Okay, so that's per photon. So that we understand is per photon. So I don't want you to try and find a unit, of per photon and say, where is it? It's understood that the energy you get from this calculation is just for a single photon. That was part A. And B is asking us, what was part A? B is asking us for the energy of a mole of photons of this radiation. So I'm just going to take this number, and Avogadro's number is really, just that. You could have Avogadro's number of potatoes if you like. So I want Avogadro's number of photons. So this was per photon, and per mole I'll just multiply it by 6.022 times 10 to the 23 moles to the minus 1. So do you see how Avogadro's number is really, it's just a number. It's a number per mole, so it can be a number of photons per mole, it could be a number of potatoes per mole, it could be a number of whatever you like, a number of atoms per mole, anything you like. And that's why the units on Avogadro's number are simply per mole, because it's whatever per mole you're talking about. So multiply this through, it'll be a much larger number now. In fact, it's 4.48 times 10 to the 5 joule per mole of photons. And you can always check in your head that that makes sense, right? If I'm going to move from a minus, when you multiply, sorry, you add your exponents. So, and of course the 7 and 6 will multiply, but it should be around 5 or 4, and it is. So that's the answer to number 2.